Okay, so what we're going to do is we're going to start working with how to take matrices or a single matrix and use what we call Gauss Jordan Elimination to put it in the form of reduced row echelon. And so I know that was a lot of terms there, but I'll show you what I'm talking about. So up to this point, there are a few things that we do know. We remember how to take a matrix, two matrices and add them or more. We know how to subtract them, right? We would say matrix A plus matrix B or matrix A minus matrix B. We also know how to take a matrix, in this case A, and multiply the whole thing by 3, so a scalar multiplication. We also know how to multiply a matrix, add it to another matrix that's been multiplied, or we can subtract it. And we have those type of operations underneath our belt. But now what we're doing is we're working with just one matrix and we're manipulating its rows inside the matrix. So the best thing to do is I'm going to do an example with you, and then I'll kind of give you some steps, and then I'll do another one and see how that goes. So the first example we're going to work with is, let's say we have a system 6x plus 6y equal to 45. And we also have 3x plus 2y equal to 19. So this is our system that we have. So this is our system of equations. And so what we want to do is, instead of using elimination or substitution, or if we were to pull out coordinate grid and graph, we're going to solve this system of equations using an augmented matrix. And what an augmented matrix looks like is you are taking all of the coefficients of the equations, of the whole system of equations, and just using those values. You're taking away the x values, the y values, any variables, as well as an equal sign or any addition signs as well. So I'll show you what we're going to do with this. So again, this is a system of equations, and you're going to take the system of equations and you're going to write it into an augmented matrix. And so what it looks like is it looks like this. So if you look at our first equation, so our first equation right here, we're going to rewrite this, and we're only looking at the coefficients. So we're looking at 6, this 6, and the 45. Okay, and you're going to see that we're going to use all of the signs that come with it too. If there's a positive or a negative, in this case, you could see our entire system of equations is all positive. So now we're going to have that first row is going to say 6 and then 6. Now, instead of these equal signs here, what we're gonna do is we're gonna separate this side of all of our equations where the operations are happening, and this side where the solutions are, and we're gonna create this line here. And so this line represents where the equal signs would have been or are. So you can see we have 6, this 6 here. This is a positive 6, this positive 6, this is positive 45, this is positive 45. And again, you can see the separation is right here with the equal sign. Now we're going to do the same thing for the second row. And so we have 3, 2, and 19. And so what we've done is we've taken our system of equations, and we have written it into an augmented matrix. And so now what we're going to do is we're going to take this augmented matrix and we're going to use what we call Gauss Jordan Elimination to create this idea. And our goal here is to create this to look something like this. 1, 0, 0, 1, and then we have some values here. And this is called Reduced Row Echelon Form. That's a mouthful. Reduced Row Echelon Form. And you might see it abbreviated as RREF. That's the abbreviation that we like to use. And again, in order to get to this, we use Gauss Jordan Elimination. So the process from here to here, I should say here, you can't see what I'm doing, from here to here is we're going to use Gauss Jordan Elimination. So Gauss Jordan Elimination, if I remember right, was, I know you don't necessarily get the history course of it, but it was developed mostly in the 1800s by two mathematicians. Well, one mathematician using the thoughts of another mathematician, and so this is where it kind of created its name. And so this is the process that we get. Now, when we get it into reduced row echelon form, and we get it here, what this is saying that this variable, whatever this represented right here, this 1, it's going to equal this value. And whatever this variable represented, it's going to equal this value. So you could see, based off our augmented matrix, when I'm talking about variables, this column represent all the x values, right? So those are all my x variables. This 6 and 2 column, this represents all of my y variables. So when we get done over here by using Gauss Jordan Elimination and coming up with reduced row echelon form, this would have said x equals whatever this value is and y equals whatever this value is. So you're solving this system, and if we were to graph it, this would be the point of intersection. This is just a different way of doing it without using all the variables. Now, it might seem daunting in the fact that we have just two equations with two variables, but it gets as complicated as having multiple variables and multiple equations. So we can get from very basic to kind of like what we have here, or a very advanced to where we could have, 3 variables are probably more common, and you might have 5 equations or 3 equations, and it gets a little bit more advanced at that point. So let's go ahead and start solving this. And what we're going to do is we're going to use this augmented matrix we've already written down, so I'm just going to rewrite it. And what our goal is to create a leading coefficient of 1. So we want this right here to be 1. And so what we're going to do by using Gauss Jordan Elimination, we're going to do what we call elementary row operations. Elementary row operations are where you'll take a whole row and you might multiply it by a number and just change it. Basically reducing the whole equation, because remember this represents equation. So we can make the equation larger, or we can scale it to smaller. We can also then use, like when we go back to our system of equations, we can multiply one row by a number and then add it to another row by changing it. And you're going to see all this develop. I know I'm talking kind of advanced here, but I'll show you. So the first thing is we want to get this to be a 1. And the majority of the time, the first thing we do when we get this to be a leading coefficient of 1, then we want to multiply that row by a number that will create that value to be 1. In this case, we have a 6. And so we like to think of, we're going to multiply by the reciprocal, sometimes opposite reciprocal, because we want a positive one. In this case, 6 is positive. So we're just going to multiply all of row 1 by the reciprocal, which is 1 over 6, so 1/6. And so how we write that is a little different as well. And so we're going to draw an arrow. And I like to write it right above the arrow, but it really doesn't matter which way you write it. We're going to say that we did 1/6 times row 1. And we use a capital R. You could use a lowercase r, but I recommend using a capital R. It's more distinguishable between numbers. And then also we use a subscript for the number of row we're working with. And so what this is going to say, that we are not changing row 2 at all. So what I like to do is I like to write the row that we're not changing. So then I know that, hey, I'm not changing it. Here it is. And sometimes we use that row in the multiplication process too, and I'll show you that here shortly. So now we're going to take 1/6 of this entire row. So we're going to take 6 times 1/6, right? So we're going to take 6 times 1/6, and we're going to put it right there. And what that's going to give us is our leading coefficient of 1. Then we're also going to take 1/6 and multiply it to this 6, and that's going to give us our leading coefficient. Not our leading coefficient, but 1. And then we're going to take 1/6 and multiply it by 45. Now that is going to give us a decimal, but that's not a big deal, so it's 7.5. And sometimes using row operations, you won't write it as a fraction. A decimal, you'll write it as a fraction or vice versa. But this one is very nice to work with. It's 7.5. If it ended up dividing by a third, then I would write the fraction because it's not a terminating decimal. So now what I want to do is, once I have my leading coefficient, which is what we have right here, I want everything above it and below it to be 0. In this case, we have nothing above, so there's nothing there. We want this to be 0. Now, what we don't want to do is we don't want to multiply row 2 by 0, because what it does, if we multiply row 2 by 0, it just essentially cuts out all of row 2. Because 0 times 3 is 0, 0 times 2 is 0, 0 times 19 is 0, and so all of a sudden we have nothing else to work with. So that would defeat our purpose, because it's a system of equations. We're trying to work with it together, not just eliminate an equation and say, oh, look, we have one equation left. So what we want to do is we're going to multiply this row 1, and then we're going to add it to this row 2. And in the process of doing that, we're going to get this to be a 0. And so how we kind of go about looking at that is we go about looking at it as, well, this is 1. What could I multiply 1 by? And then add it to 3 and get 0. So we always think we want to multiply that 1 that we're working with by the opposite of the other parts that we want to make 0. So this is 3. What's opposite of 3? It would be negative 3. So what we're going to do is we are going to multiply row 1 by negative 3, and we're going to add it to row 2. Now I want you to pay attention to the order in which I just wrote that. So I get in the habit of always writing the row that I'm changing last. So I'm changing row 2, so I can look through my work and say, what did I change? Because there might be sometimes you want to change more than one in one from one movement. In this case, we're just going to work with one row at a time. But when we have a 3x3 matrix or a 3x4 matrix, or we have all these different size matrices, sometimes we can do row operations more than one in one movement. So it's a good habit to stay organized in your work. And so how I do it is I always say the row that I'm changing is always my last row that I write. So now, remember, I'm not changing row 1, so I like to write it. I like to know that I'm not changing it and it is 100% staying. So now that I take row 1 and I'll multiply it by negative 3, then it looks like this. This really looks like negative 3 plus 3. That should give me the 0 right here. And then now I have negative 3 times 1, which is negative 3 plus 2 gives me negative 1. And then I have negative 3 times 7.5. And what that's going to do is that's going to give me a little bit of a larger number, right? And so negative 3 times 7.5 is negative 22.5 or negative 22.5. So I'm going to take this negative 22.5 and add it to 19. And that's going to give me a negative 3.5. So you can see we're slowly getting to our goal here. Our goal is to get it in reduced row echelon form. So we have a 1 and the zeros. We have a leading coefficient of 1, and we have the zeros above and below it, like we have here. Now our next goal is to get this. We go down the next row and the next column, and we get that to be a 1, which would be this negative 1 that I've circled here. So in order to get that to be a positive 1, we want to think, again, we want to go back to what we did here. When we looked at our very first thing is we wanted the 6 to be a 1, and so we multiply by the reciprocal. But I also mentioned we multiply by the opposite reciprocal if that value that we started with was negative. In this case, our 6 was positive, so we just multiply the reciprocal. Now, we have a negative, so we're going to multiply by the negative reciprocal. And the reciprocal of 1 is just 1. So what we are doing is we are going to multiply this second row by negative 1. So we're just going to say negative row 2. And notice how I'm going to the next line, and you can rewrite it. Some will rewrite this whole thing down here, and you can. That's perfectly fine. But I'm just going to pretend like I'm just going to keep going. So I'm going to take and multiply row 2 by negative 1. And so remember, I'm not changing row 1. I think I just said multiply negative 1 by row 1. What I meant was negative 1 to row 2. And so now my row 2, if I take negative 1 and multiply by 0, I still get 0. When I take negative 1 and multiply by negative 1, I get a positive 1, which is what we wanted. And then when I take negative 3.5 and multiply by negative 1, I get a positive 3.5. Now, just like we did before, once we got the leading coefficient of 1, we wanted everything above and below to be zeros. So now we have the next leading coefficient of 1, we want everything above and below to be zeros. Well, now because we have no row below, then that's checked off. We want this to be a 0 right above it. And so in order for that to happen, we do the same thing we did here. We're going to figure out what can we multiply this row by, and then add it to this row to be this right here, a 0. Now the reason why we do it in this order is because no matter what I multiply this 0 by, I can multiply it by 1,000,000. And if I add it to this row right here, this is still going to get back 1 because 1,000,000 times 0 is 0, and 0 plus 1 is 1. So this will not change. That number won't change. That's the point of us find the leading coefficient and then the zeros above and below it. That way when we go back to do other rows and get those leading coefficients, then we don't go back and change what we've already done. So now what we're going to do is we're going to multiply this row right here by negative 1. When we multiply this by negative 1, this gives me negative 1, and then when I add that to 1, that's going to give me 0. So we're going to say that we're going to multiply negative row 2, but then we're going to add it to row 1. Remember the order that I write it in? The way that we wrote it right here, it shows that we are going to change row 1. We might be doing some operation in row 2, but row 1 is the one that we're going to change. So I'm going to rewrite my row 2. That's the one that I'm not changing. And then when I go about and do this, remember, negative times 0 is still 0, plus 1 is just 1. And then negative times 1 is negative 1, plus 1 is 0. And so that 0 is going to go right here. And then the last part, which gets a decimal with you, right? And you're going to say negative 3.5 plus 7.5. That's going to give you back 4. And so what does this mean? This means that our x value is 4 and our y value is 3.5. Where did I get that from? If you recall, when we did this, we said that this column represents all of our x values. So I should only have one, that messed up. I should only have one row that has a 1 there, and that will be what that variable represents. So this is our x column. So our x column, so here's our 1, so that means that x equals 4. This column is was our y's. This means that y equals 3.5. This is 0, so this has nothing to do with it. So this is the point of intersection when we are dealing with these two equations together. So recall kind of what our process was. Our process in this whole situation is to get, and I'm going to write some steps down, but they're going to be very repetitive. So our first step, once we have it written as an augmented matrix, is we're going to get a leading 1 or coefficient of 1 in the first row. once we get the leading 1 in the first row, then our next step would be to get zeros in all rows for the column. So basically zeros above and below that 1. Step 3, we already did step 2. Step 3 would be to get a leading 1 in the second row. And there's more advanced movement to this as you keep progressing, but we're taking steps to get there. And so we're not going to worry about, you might find something about switching rows and things like that, but we're not quite there yet. So we're going to take these steps to get there. And then once you get a leading 1 in the second row, then you're basically repeating step 2 by you're going to get zeros in all rows for the column. And what's going to basically happen is we're going to repeat. We're going to keep repeating until we run out of rows to get leading coefficients of 1 in, and then we have solved the system in a matrix form. So I'm just going to say repeat. Okay, so I'm going to go, I think I can just add a page here. All right, so here we go. We're going to go to our next example. So our next example, let's say we have the equation or the system of equations 2x plus 4y equal to 0. And we have 3x plus 5y equal to -2. So again, this is our system of equations, and we want to write it as an augmented matrix. And so how we write it, again, it's just using all of the coefficients, and we use all the same values, like the positive, negative part of it. And then we're also going to create this vertical line to represent our equal signs. So when we do this, we're going to say 2, 4, 0, 3, 5, -2. Now, if you want to pause this and try this on your own, this would be a great time to do that. But if you want to follow along, I'm going to work through it. If you pause and work on your own, then come back and you can hear me work through it as well. All right, so our goal again is to get this to be a leading coefficient of 1. So this 2, we want it to be a 1. So we want to multiply by its reciprocal, and if it was negative, we would multiply by its opposite reciprocal. In this case, it's positive. So we're going to multiply row 1 by 1/2. And so we get 1. 4 times 1/2 is 2. And then 0 times 1/2 is 0. And remember, we're not changing the second row, and usually I do write that first. But I was getting anxious to do that elementary row operation. Next, what we want to do is, since we got the leading coefficient of 1, we want to make zeros all below it. In this case, we don't have an option above, so that's why I said below. So we're going to take that first row, and we're going to multiply it by the opposite of whatever that is. In this case, it's the opposite of 3 is -3, so we're going to take -3, multiply it by row 1, then we're going to add it to row 2. And remember, we write row 2 second because that's the row that we're going to change. So I'm going to rewrite row 1 because we are not changing that. And then I have 1 times -3 plus 3. This will give me 0, so I get to put 0 right there. Now I have -3 times 2. -3 times 2 is -6. -6 plus 5 is -1. I'm going to put that right there. And then lastly, I have -3 times 0, which is just 0. So I get 0 plus -2 just gives me back our -2. So now we have found the leading coefficient of 1 and made everything above and below at 0. Next is to make our next row leading coefficient of 1. And so we're going to take our second row and we're going to multiply it by, remember, it's the opposite reciprocal. Well, really, it's the reciprocal, but opposite because it's negative. In this case, the opposite reciprocal of -1, again, it's like we did in the previous problem, it's just -1. So we're going to multiply row 2 by -1. We're not changing the first row, so I'm going to rewrite it. And then simply put is that our signs in the second row are just going to change. So 0 is still 0, -1 is 1, -2 becomes 2. Now that we have a leading coefficient of 1, we're trying to get the other rows above and below that to be 0. So we're trying to make this become 0. In order to do that, we're going to multiply our leading coefficient of 1, so our leading 1, by the opposite of whatever number that is. So in this case, we're going to multiply row 2 by -2. And remember, we're changing row 1. So when we rewrite this, we're not changing row 2 anymore. We have 0, 1, and 2. And then when I take and I multiply this entry by -2, this gives me just 0, right? So 0 plus 1 is still 1. This is why we do it this way, so we don't go back to undo the things we've already done. And then I'm going to take this one, multiply it by -2, so I should over here, -2 plus 2, this will give us 0, and we're going to write the 0 right there. So 0. And then next we're going to take this -2 here, multiply it by this 2, so this gives us -4, and then -4 plus 0 is just -4. So now we are done solving this because we have reduced row echelon form, meaning that we have a leading 1, 0 is above and below, and then in the next leading 1, 0 is above and below until we run out of room. And so what we call this also is we have a diagonal of 1s. And so then once we do that, then we can go through and say that x is -4, because remember this represented our x values, this represented our y values, so if x is -4, then y is +2. Now this does get a little more complicated when we have more rows, more variables, but this is our basic of what we're going to be doing in solving matrices or a matrix using elementary row operations.